So yeah, thanks a lot for having me here. I'm Peter Kraus from ETH Zurich. I'm working in a group of Hans-Jakob Werner, and today I'm going to talk about our results on attosecond charge migration and its laser control, which we decode by means of harmonic spectroscopy from the harmonic generation spectra. In general, ultra-fast electronic dynamics are abundant phenomena in nature. So, for example, some wave-like energy transfer and photosynthesis in this Fenner-Matthews-Olsen complex has been observed by multidimensional electronic spectroscopy, and the electronic coherences have even been invoked to explain the unusually high efficiency of photosynthetic light harvesting. In order to understand these processes, to eventually even control or manipulate them, we have to find methods to follow them. And there are a few very nice methods out there to follow these electronic processes. And one method would be transient absorption spectroscopy, which is in principle capable of following both populations and phases of states in the cation. However, right now it's still limited by the pulse duration of the involved infrared pulses. Another technique would be harmonic spectroscopy that relies on the subcycle timing resolution of the electron trajectories in the process. Till now, in this example of CO2, it was mainly used to compare with theory, to benchmark it. And another way would be photofragmentation spectroscopy that we'll hear about in this conference, which is also limited by the pulse duration of the infrared pulse. So in this talk, I'm going to focus on the part of harmonic spectroscopy to learn something about the time evolution of states directly from the observables of harmonic generation. So let's have a bit of a closer look at harmonic generation, what does happen in this process. It's typically understood in a model where the laser field tunnel ionizes an electron, and the electron is accelerated by the laser field and driven back, and upon recollision, all the XUV, the attosecond light burst, is emitted. This is typically done in a multi-cycle field, so it's repeated every half cycle, and then what we observe in the spectrum is a column of odd harmonic frequencies. Let's take a bit of a closer look in what happens in one half cycle of the laser field. So if we zoom in here, we find that we have discrete electron trajectories within one half cycle of the laser field, and they are defined by a unique time of ionization and time of recombination. And depending on how much time now the electron spends in the continuum, it gains a certain amount of kinetic energy, which then gives rise to a certain photon energy, which is emitted, meaning this electron trajectory here will correspond to a unique time that the electrons spend in the continuum, and will give rise to a certain emitted photon energy. So we have a one-to-one mapping between photon energies and transit times. Now the idea is to use that as sort of a unified pump-probe scheme, where the ionization step can launch electron dynamics, like an electronic wave packet, which is then probed by the recolliding electron in the photorecombination step. And this idea has been already successfully used to probe nuclear dynamics, an evolving nuclear wave packet after ionization. If we do that for 800 nanometer, shown here again, we typically can access transit times that are about 1.7 femtoseconds. This is always defined by the duration of one laser cycle. So if we do that with a longer driving wavelengths, for example, with 1300 nanometer, we can go to up to 2.8 femtoseconds. That means by scanning the laser wavelengths, we're now able to access different transit time windows that we can use to observe the dynamics. So much for the concept of using this process of harmonic generation as self-probing of electronic dynamics. What's the system we want to investigate? And this is shown here. This is iodacetylene. This is HCCI, the molecule. And we chose it because it has some very interesting and relevant properties for us. So it has two rather closely lying excited states in the cation, the ground state and the first excited states. They are spaced about 2 electron volts and both significantly populated by strong field ionization. However, the next states that are all further apart here, the sigma and pi states, are not strongly populated by strong field ionization, which was revealed by TD-DFT calculations by André Bandraug. Apart from that, we only have 2 states that are getting significantly populated. They are also coupled by a very strong transition dipole moment, which lies along the internuclear axis. This means if we now manage to align the molecules parallel to the laser field polarization, we can very strongly drive the population transfer. We can shift populations from one state in the other one, or vice versa. However, if we would align the molecules perpendicular to the states, we can completely switch out this dipole coupling and observe a quasi-field-free evolution of the states. In that sense, orientation is our switch to laser-controlled dynamics. What we are now looking for is to reconstruct the quantum dynamics between these two states in terms of their populations and phases. And we do that by measuring the harmonic generation amplitudes or intensities and phases, and then try to invert it to directly these populations of the states. So let's look at the data. We start with harmonic generation experiments of oriented iota-acetylene molecules. We orient the molecules with a two-color laser field to generate an oriented rotational wave packet and then generate high harmonics from these molecules. Because of the broken inversion symmetry, this leads to the emission of even harmonics that are also shown here on the detector. You see these weak even harmonic components in addition to the odd ones. Here's the spectrum for iota-acetylene shown, and you see in the red spectrum is the oriented spectrum. We have the clear emission of even harmonic frequencies, and another way to plot that would be always to take the ratio, the emission ratio of the even harmonics divided by the mean value of the two neighboring odd harmonics, which is shown here. This would be the first observable. Next one would be to rely on intensity measurements now of the odd harmonics. You can follow the odd harmonics as a function of the pump-probe delay between the orienting pump pulse and the harmonic generation probe pulse. And at the timing of the orientation, which is given by the rotational constant, the molecules are aligned, they are fixed in space. This is typically rationalized by this expectation value of cosine square theta, which is shown here, calculated theoretically. When this value minimizes, it means that the molecules are aligned perpendicular to the field, and afterwards it maximizes, so they are aligned parallel to the field. The low harmonic orders modulate exactly like this expectation value of cosine square theta, but then it flips, and the high harmonic orders modulate opposite to it. Another way of plotting that would be to take the ratio of the emission of parallel alignment divided by the emission of perpendicular alignment. This is shown here, blue line for 800 nanometer. Whenever this line crosses unity, it means the reviver flips. And in addition to that crossing, we actually see that there is a minimum in this ratio at 800 nanometer. We can do exactly the same measurement with a driving wavelength of 1300 nanometer, and we see the beginning looks similar, but then it deviates. And actually, we see a minimum at rather around 35 electron volts. Remember what I said before. I said what we can do by changing the wavelengths is changing the mapping between photon energies and transit times. And that means now that by changing this mapping, these photon energies can correspond to a different transit time. This can be seen as a first indication of Hall dynamics, because when there's a minimum at a certain wavelengths that can originate from a different, from a dynamical origin, like a time-dependent electron-hole wave function, this should exactly change its position in the spectrum when you change the wavelengths or also the intensity. But the effect with the wavelengths is typically stronger. Another observable that we can consider are phase measurements of high harmonics, which is shown here. So what we do is we generate two high harmonic generation sources that interfere in the far field. We do that by imparting a pi phase shift on the fundamental driving beam. Then we let the two sources interfere. This gives rise to fringes in the far field, shown here, it's zoomed in. Then we align only one of the two sources, rotate the alignment direction, then see how the fringes shift as a function of the polarization, of the alignment of the molecules. And from this fringe shift, we can determine the phase modulation of the different harmonic orders as function of alignment angle, which is shown here. The experimental data fitted with a series of Legendre polynomials. And we see that, first of all harmonics have show very different behavior as a function of the alignment angle in terms of their phase evolution. So these phases really modulate very differently. And if we now again compare 800 and 1300 nanometer, the two same colors correspond to roughly the same photon energy. For example, we see practically no modulation at 17 electron volts for 800 nanometer, but a very strong one for 1300 nanometer. So again, we have a strongly driving wavelength dependent phase, which is another indication for Hall dynamics. Now, we don't want to stick with the idea now that we can only see these indications of the Hall dynamics. We rather want to reconstruct it from the experiments. So what we do is we formulate an expression for the high harmonic emission dipole moment, which contains the initial populations as prepared by strong field ionization, the nuclear autocorrelation functions. This accounts for nuclear dynamics in the cation after ionization, propagation phase, final populations of the excited states, and for the recombination dipole moment to account for that last step in high harmonic generation. And based on that expression, we can now formulate the underlying equations for all the experimental observables that I showed you before. And what we then do is calculate for the recombination and propagation phases and the nuclear motion from theory and invert the expression to get the initial and the final populations of the states that are involved in the dynamics to describe the dynamics from the observables of harmonic generation. And this is what we get for the perpendicular orientation, so for the rather quasi-field-free case. We find a population amplitude of about 0.9 in the ground state and roughly 0.4 in the excited state. And within the lower limits of the error bars, this is coming close to predictions of the weak field asymptotic theory or the TD-DFT calculations. In addition, this also comes with a relative phase between the two states. This phase is close to 0 for perpendicular alignment, and this phase, together with the initial populations, now lets us reconstruct an initial hole after strong field ionization, which is shown here. So we have a hole that's mainly localized at the iodine end of the atom, and then given by the energy separation between the eigenstates and the cation, this hole does a time evolution, and it comes to the acetylene end of the cation and then back after 1.9 femtoseconds. Interestingly, for parallel alignment, this initial phase is almost out of phase by pi, which would correspond to a hole at the acetylene end of the molecule. I'm not going into detail in that now, but certainly a very interesting effect here. So this was the case for the perpendicular alignment. Now let's look at the parallel alignment and the final populations we have for the parallel alignment. So in that case, we have a very strongly driven population transfer between the cationic states. So what we get is a very strong depopulation of the ground state in the cation that is then slightly repopulated, shown here, and the phase at the time of maximum depopulation actually jumps. And when we do the same for 1300 nanometer, we see an extremely different behavior with a strongly depopulated phase and then a repopulation. In that sense, the driving wavelength has a very strong influence on how the population transfer in the states occurs. Now, because we have amplitudes and phases of the states, so there's always a fractional population, a relative phase between the excited states, we can reconstruct the full quantum dynamics in the iota-acetylene. This is shown here for 800 nanometer. So while there's not so much happening in the time window of observation for the field-free dynamics, there is a lot of motion in the case of laser control dynamics, where the laser field really pushes the hole along the acetylene unit very rapidly. In the case of 1300 nanometer, there's a bit more charge motion happening for the field-free case. And for the laser control case, the laser field really localizes the hole at the iodine atom first and then pushes it back and forth. Okay, so this is what we reconstructed with the scheme from our experimental data. Now we, of course, have to compare that to theory. And what we do is comparing that to a bound state TD-DSE calculation, which we did for 10 and 2 states, and surprisingly enough, they agree for the simple reason that we really have these 2 states that don't talk with the rest of the excited state manifold. And this is what we get from the simulation. So the case for 800 nanometer, the strong depopulation is pretty much recovered also in the theory at actually exactly the same timing than the experiment. And also the phase jump is recovered, it's just a bit less pronounced. And also for 1300 nanometer, the strong repopulation is, that we see here in the data is recovered. It's, however, occurring at a different time at rather 1.8 than 1.5 femtoseconds. So this is the state of what we're having here. What we did in this experiment is to do what we consider complete harmonic generation experiments in terms of phases and amplitude, used all these data together in a generalized theory to reconstruct both the field-free and the field-driven dynamics in the cation. And as a next step, we would definitely take that to further molecules to see if that's generally applicable, which we certainly think right now. So thanks a lot for your attention.